Let's look at two other discrete probability distributions, the Poisson and the Hypergeometric. And we'll look at these relatively quickly. The Poisson distribution is used when we try to describe events that occur over time, in an interval of time, or in volumes or areas or spaces. So typically in business, we're interested in, say, the number of customers arriving in a period of time, or some other events that occur per year. And there are some percentages or probabilities or average percentages associated with these occurrences. So we're going to count the number of times an event occurs in an interval or in a unit of measure. And the assumption that we make is that the probability is the same for an event for all units. So it's always the same probability that we're using for this event to occur. All the events are independent, and the mean number of events in each unit of time is denoted by this symbol called lambda. This is the formula used for the Poisson probability distribution, and we see that the main things that we need to know are the mean, which is the expected number of units that's typically given, and then this value x, which is the probability that we're looking for. So we're looking for the probability of x given this mean. So it's really pretty simple. It's just that we have to use these exponentials and a factorial. So it gets perhaps kind of confusing. The standard deviation is lambda. Sorry, the variance is lambda, and that's also the mean. The mean is lambda. So it looks like this. If lambda equals 6, it looks a little bit more normal. Here's an example. Customers arrive at a rate of 72 per hour. What's the probability of 4 customers arriving in 3 minutes? Well, we need to convert 72 per hour into minutes, and then we can apply that formula. And this is a typical situation. So 72 per hour is 1.2 per minute, or 3.6 per 3 minutes. And that's what we're interested in, is this 3-minute interval. That's the question. We're arriving in 3 minutes. So the average, lambda, is 3.6. And this is the formula that you would use. If you like to use Excel, here's what it would look like in Excel. Here's x. This is how you denote the factorial, or find the factorial of x. The mean is given, or you calculate it, that's the lambda. This is how you raise lambda to a power. So mean to the x power. That's what I've got there. That's the mean to the x power. This is how you do an exponent. That's e to the, in this case, negative mean power. And then this is the probability. This is the d3, which is the mean to the x power. I'll scoot this up a little bit. That's this part times e3, which is this part here, which is e to the minus lambda power, divided by b3, which is the factorial. So you can use that. It's useful sometimes. If you like Excel, Excel can be very helpful. If I wanted to find some other probability, let's say what's the probability that 3 customers arrive, well, I just put 3 in there in the next 3 minutes. What's the probability that 6 customers arrive in the next 3 minutes? So it gets less. So that's the advantage of Excel. You can just put in some new numbers, and there they are. You can also look it up in a table. There's a table in the back of the book that has all these probability distributions. And you should know how to use these tables, because we're going to use them really quite a bit when we go to continuous normal distributions in the next portion of this lecture. So I'm going to go pretty quickly through this. You should work this on your own. I'm not going to lecture on this, but you basically have to convert to a mean and then just plug the values into the formula. There's another commonly used discrete distribution. It's called the hypergeometric, and it's kind of like the binomial, except that we're going to draw elements without replacement. In other words, we have this dependency. It's like if I had the bag of red balls and blue balls, and I start pulling them out, and I'm asking you what's the probability of getting 2 red and 1 blue, or something like that. Well, what you've pulled out in the past affects the future. So that's this without replacement, and it creates a dependency. This is the formula, and I probably won't ask you to use this because I really want you to use Excel, and we don't have access to Excel in this class. So let's go on to continuous probability distributions, the probability distributions for continuous random variables. And the most important one that we will deal with is this normal random variable. So this looks normal. It says it's nice, symmetric, mean equals median equals mode, shape. And it's a smooth curve. It's not discrete. It's a smooth curve. Those others we were looking at had a discreteness to them. So this curve is called a probability density function. It has different names, a probability distribution. I like that last term. It's a distribution of probabilities, and the actual probability is determined by the area under the curve. And that's why sometimes you use integral calculus, but we won't use integral calculus. We'll just look things up in a table. So the area between A and B is the probability that X assumes a value between A and B. By the way, that does not include A or B. So the normal distribution, sometimes called a bell curve, sometimes called a Gaussian curve, is very useful. So many processes can be described using this normal distribution. And we can use it to approximate the binomial distribution. And it's the basic for classic statistical inference, which is what this class is about. It's classical statistical inference. It has this nice bell-shaped symmetric curve where the mean and the median and the mode are all the same, and it's symmetric. Very useful. It's also called a Gaussian. This is the formula that creates that curve, but we won't use this formula much. We'll use this Z. We're going to standardize this thing. This is, if you recognize that, that is the formula for finding Z. And then we'll look it up in a table. So if you change the mean, it shifts it to the left. If you make sigma bigger, the variance, or sorry, the standard deviation bigger, it spreads out. It creates more dispersion. And we're looking for the area under a curve, and that's the probability. Probability is area under curve, and here's some integral calculus. And we'll just, like I say, we'll just look this up in a, we'll standardize, and then we'll look it up in the table. So by standardizing, we mean that we're going to use this one table that has a mean of 0 and a standard deviation of 1, and all we have to do to get that is transform whatever numbers, whatever means and data points we're given to a Z. And you did that on the last test, and so we'll use it again this time. So we'll have these values for Z. So the probability that Z is between 0 and 1.96 is right here. And if we look this up in a table, 1.96, it's 0.475. And if we doubled that, that's about 0.95. And that's about plus or minus 2 standard deviations. So we'll use that idea again and again and again. So in the table in the book, the table will give you the area to the right of 0. And since it's symmetric, it's also giving you the area to the left of 0. So if we want to find the area under the curve, which is the probability that z is between minus 1.26 and plus 1.26, we would draw this little graph here, and we'd look out 1.26, and we'd look it up in a table, and we'd get this value here, and we'd come up with about 80% is the probability that x is between these values. What if we wanted the probability that z is greater than 1.26? Now we could subtract this number here at 3962 from half to get the remaining value. So this is how we'll do it when we look it up in a table. Same way if it's on the other side. If we're interested in this interval here, that it's between negative 2.78 and 2, we'd subtract the 2 and get this difference. So we calculate the 1 value of 0.4973 and then 4772, and the difference is that area under the curve that I'm interested in. And so we'll do lots of examples where we have to use the table to look these up. So if we looked up in the table, that area corresponding to z being that far away from 0 is that value, 4834. Then if we add a half, the area to the right of 0 is 1/2. The total area under the curve is 1, and exactly half, starting at mu equals 0, either side is 1/2. So I said that not quite right, but from this area on to the right is a half, and from this area on to the left, area under the curve is a half. Now notice in all these that they've exaggerated the shaded area, because this would be a little bit further. Anyway, they want to make a point there. So that's the probability that it's greater than negative 2.13. If we have non-standard normal distributions, which we usually do, usually distributions don't have a mean of 0 and a standard deviation of 1, you need to transform them. If we didn't, we'd have to use calculators all the time or create a whole bunch of tables. Well, we can create one table if we simply transform the data point that we're interested in, finding the probability of, transform it by that formula that we've used before. Z equals the data point minus the mean divided by the standard deviation. After you do that, you can look it up in a standard normal table. So that transforms a normal distribution into a standard normal distribution. Here's the mean, here's a standard deviation. And by doing this, we can transform the values into a mean of 0 and standard deviation of 1. And we have one table. That's all great. So what you want to do when you work these problems every time, always, consistently, so I'm trying to make a point, is sketch the distribution, indicate the mean, and shade the area corresponding to the probability you want. It's very important. It goes a long ways. And then convert the areas from an x value that you start with to a standard normal value by doing this simple little trivial change of x minus the mean divided by the standard deviation. So you then show the z values under the corresponding x values and look them up in the Appendix A table, and always use symmetry. It's going to be very useful. And of course the idea that 1/2 of the area under the curve to the left or to the right is 1/2. So this is a half, that's a half, total of 1. So there's a mean of 5, standard deviation of 10. We transform that. And in this case, we're transforming 6.2. So how far away is 6.2 from 5? It's 0.12 standard deviations away. So 6.2 is 0.12 standard deviations away from the mean of 5. And the area under the standard normal curve from 0 to 0.12 look that up in the table, it's 0.0478. So you look that up in the table and that's what you get. Here we have the same standard deviation and mean, but we have a different data point. And so it's kind of nice that that's the mean there. We only have to look up one value. In the next slides, we'll look up more than one value, or we'll transform more than one value to look up. So with symmetry, this is the same as 0.12. So it's 0.0478. So the same thing, whether it's 6.2 or 3.8. They're both 0.12 away, and that's the same area under the curve. So here's a slightly different. We want to go from 2.9 to 7.1. It's nice that it's the same distance away, 0.21 away, so I can just look up one value and then double it. And if I was to look this up, actually if I was to look that up in the table, I'd get 0.0832, and I doubled that. So this is the good thing about drawing these curves. So once again, we're starting with a mean of 5, and we are interested in what's the probability that x is greater than or equal to 8. Well, 8 minus 5 divided by 10 is 0.3. And if we look up 0.3, we would get 0.1179. Well, we want the area to the right. That's why we draw those pictures. We want the area to the right. And that area to the right is 0.5 minus 0.1179. And that gives you that 38% probability. And here we'll do a similar kind of idea. You transform 7.1 and 8, and then we look up those values in the table and take the difference of them to come up with the area under the curve, which is the probability. So here's an example, and I think I'll stop this lecture. The example is you work for quality control. You have a light bulb that has a normal distribution. Its life is normally distributed. The mean is 2,000 hours, and the standard deviation is 200 hours. What's the probability that a bulb will last between 2,000 and 2,400 hours? So we'll calculate how many standard deviations is 2,000 away from 2,000. Well, it's 0. And how many standard deviations is 2,400 away from 2,000? Well, it's 2. 2 times 200 is 400. And we'll then look that up in the table. So we want to graph it. There's our little graph. This is the probability that we're interested in. We transform it. It's 2 standard deviations. We look up 2 in the table. That's 0.4772. So the probability that the bulb will last between 2,000 and 2,400 is about 48%. What's the probability that the light bulb burns out before 1,470 hours? Well, we do the math. We transform 1,470 to its normal, standardized normal counterpart. We get minus 2.65. Well, that's the same as 2.65. And then we subtract we subtract this 4960 from a half, and that leaves this little area here. It's exaggerated, by the way. And that little area there is 0.004. So 0.4%, a very small percent. So I think I'll stop there and continue this lecture later.